This whole first page, we actually have already done. We did this in Algebra 2, if you remember, with matrices. This is mainly what we did when we did matrices in Algebra 2. We just used matrices to help us solve for linear equations. Now, we kind of like brushed over, well, I mean, I tried to teach the why, but I think many teachers in Algebra 2 kind of brushed over how or why we did what we did in the calculator to solve for matrices. So I just want to quickly explain why we do what we do. If I'm looking at this equation right here, A times X equals B, without knowing any background information about what this means, how would we go about solving for X? Without trying to figure out, yes, okay, yes, I'm like, what? Without knowing exactly what this means, in order to solve for X, we need to get the A off of the X, right? So we divide by A. Well, now if I tell you, okay, these are actually matrices, and I'm telling you you can't divide a matrix, what can you do instead? Instead of writing this, how else can we write the division of A without actually dividing by A? What's another way to represent A no longer in the denominator, but it means the same thing as dividing by A? Yes, Isaac, yes, exactly. Remember, guys, I don't know where to write it, but when we are dividing by something and we want to get it out of the denominator, it means the same thing as the inverse of that denominator, or the negative version of that exponent on the denominator. So we can do the same thing over here. If it'll scroll. Instead of dividing by A, we're going to take the inverse of A on both sides. Now, A times the inverse of A, this means the same thing as A divided by A. They cancel, leaving us with just X is equal to the inverse of A times B. Now, this A matrix is called our coefficient matrix. It's the coefficients on the variables in the linear equations. The X represents our variable matrix. And the B is our constant matrix. It is what our linear equations are equal to. So, if I'm looking at this example here, according to the circuit diagram, the currents I1, I2, and I3 in amps are the solution of the linear system. And we're given these linear equations. In order to solve this, I can apply matrices. Now what I need to do is take the coefficients on the variables and separate them from the variables, creating a coefficient matrix and a variable matrix. So my I1s are going to be my first column. My I2s are going to be my second column, and my I3s are going to be the third column. They all have to line up. They have to be in the same order. So the coefficient on the I1 is 2. So that's where that 2 came from. The coefficient on I2, oh, there is no I2, so I write down a 0 for that coefficient. And the coefficient on I3 is 4. And I just continue in the same fashion. I have 0 for I1, I have a 1 for I2, and a 4 for I3, 1, 1, negative 1. And then I write down my variable matrix of I1, I2, I3. Now, if we remember back yesterday or last class, When we think about multiplying matrices, remember, you're multiplying the rows of the first times the columns of the second. So how this will actually multiply out is the first entry in the first row times the first entry in the first column. The second entry in the first row times the second entry in the second column. And the third entry in the first row times the third entry in the first column. This is why we can use matrices here, because of the definition of matrix multiplication. It doesn't work like normal multiplication would work. You multiply the row times the column. Do you need to know that? No. It's just, why does it work? That's why it works. All right. Then you set it equal to the constant matrix. So this is like our A, this is our X, and this is our B. So in order to solve this linear system, what you do is you set the variable matrix equal to the inverse of A matrix times the B matrix. All we did, we multiplied both sides by the inverse of A, and this is how we can solve for our variables. Last class, I showed you guys how to do this in your calculator. Now, in this second example here, not second example, but the second step, they've actually already inversed A. They're just showing you it inversed. We're going to just type in the original and make our calculator do the hard work. Now, to get the to get the matrix, does anyone remember what I press? What do I press in my calculator? Alpha zoom. Wonderful, yes. Also, for those of you that don't have calculators, I realized that Desmos has a great matrix calculator that you can use. So if you don't have a calculator, you literally just type in Desmos matrix, and it is a beautiful calculator that works just as well. Yay. All right, so back to it. We press alpha zoom. Now this is a 3x3. And again, I told you I'm going to input the original and make the calculator do the work. Because we are virtual, we do not need to do this by hand, which is great. Most of this, if we weren't virtual and we were in person, most of this we wouldn't make you do by hand, most of it. But then remember, we have to inverse this, so we just press that inverse button, that -1 exponent. Then we multiply it by the constant matrix, which is a 3x1 matrix. 24, 23, and 0. Press enter. Ugh. There we go. Press enter, and we get 2, 3, 5. Which means that this first entry in that column is what our I1's amps are. So I1 is equal to 2 amps. The second entry in the column is I2. That is 3 amps. And the third entry is I3, which is 5 amps. And we have solved the system. Could you have done this with substitution and elimination? Yes, you could have. Just like we learned in the beginning of Algebra 2. But matrices make it so much easier, so much nicer, quicker. Are there any questions on this? Okay, beautiful. So now, let's try it again. in this word problem. The Jones family invests $10,000 in bonds and wants $760 annual return. AAA rated bonds average yield is 6.5%, A rated bonds average yield of 7%, and B rated bonds average yield of 9%. The Joneses invested twice as much in bond B as bond A. Let X, Y, and Z represent the amounts invested in AAA, A, and B bonds, respectively. Use the inverse of the coefficient matrix to find the amount invested in each type of bond. Now, most times in a word problem like this, they won't give you these equations. Everything that I just said gives you the equations in word format, and you would have to create the equations. You've done this before, did it in Algebra 2. It's not too tricky, it's just you have to do some reading. Okay, no big deal, I hope. But lucky enough for us, for this first one, they do give us the equations, so let's just go ahead and solve it. We first convert this into matrices by taking our coefficients and placing them in one matrix. So here we have 1, 1, 1, 0.065, 0.07, 0.09, 0, 2, -1. And this is multiplied by our variable matrix, set equal to our constant matrix. So now to solve, this is, let me show you, our A matrix, our variable matrix, and our B matrix. To solve, we just do the inverse of A times B. So I press alpha zoom. This is a 3 by 3. 1, 1, 1, 0.065, 0.07, 0.09, 0, 2, -1. We're inversing it, multiplying it by the constant matrix, which is a 3 by 1, 10,000, 760, whoops, 760, and 0. And we get 4,000, 2,000, 4,000. Meaning 4,000 in AAA bonds, 2,000 in A bonds, and 4,000 in B bonds. I'm sorry I'm not, I normally ask way more questions than this. This is not a very question-heavy day. It's just me doing and showing you guys what to do. Does this make sense? Honestly, you guys had no problems with this in Algebra 2, so I hate to assume that you're not going to have issues with this, but I tend to want to assume you won't because you didn't in Algebra 2. Okay, cool. Cool, cool. All right. So now we're getting into stuff we didn't do. There is another way to solve for matrices that does not include making the coefficient matrix inversed times the constant matrix. And the way to do this is by taking a matrix, putting the coefficients and constants all in one matrix, and then putting it in what is called row-reduced echelon form. Now, what row-reduced echelon form is taking a matrix. So say we have this matrix. And all of the first 3 columns start to look like an identity matrix, with ones on the diagonals and zeros everywhere else. And then the last column produces 3 numbers. Now these numbers, once this is in row reduced echelon form, represent the solutions to the variables. Now you can do this by hand, and I believe that we made you do it by hand in Algebra 2, by doing what is called Gaussian elimination. Remember where we had to like multiply rows by other rows and subtract rows from other rows and double rows and divide rows until we got ones on the diagonals and zeros everywhere else. We're not making you do that this year. I hated that. You will have to do it if you take linear algebra in college. You will have to do it, but we're not doing it in pre-cal. We're making your calculator do it, okay? So, to make your calculator do it, first you have to press, and it says it all right here. First you have to press second, and then the inverse button, which has matrix written right above it. And you go over to math, and you go up to RREF, which stands for row reduced echelon form. On Desmos, there's literally just a button, like immediately on that matrix calculator that says RREF. That is row reduced echelon form. Once you do that, we're going to enter our matrix. So this matrix in our example is a 3 by 4. And we have a -3, -2, 1, 6. That line there in the middle of the matrix just denotes that we're kind of like combining what were originally 2 separate matrices together. It's not something that needs to be shown in the calculator. It's just so that our mind has an easier time understanding what's happening in this matrix. Our calculator doesn't need it. So then we have -1, 0, 2, 4, 9, 8, 3, -2. And boom, we have our answer. So I'm going to go ahead and erase what I put in numbers here. And I'm going to put the actual numbers. 16, -22, 10. What this means is x is 16, y is -22, and z is 10. And I'm done. It's just a separate way that you can solve for matrices. Solve for variables, I should say, within matrices. Any questions on this so far? Okay. So now, there are on this page 2 different types of problems that they're going to ask you versus just solving a simple linear system of equations. They could ask you to take 3 separate points and fit them to a line. So you're basically creating a line from 3 points. Now, you might be saying, but Miss Sunderland, last class you told us that matrices can only be used with linear equations. This is the exception. Because we're only actually dealing with a single line. It's not 3 separate lines like this problem showed us, right? These are 3 separate linear lines. Because we're only dealing with a single line, but creating 3 equations that represent that same line, you can use matrices to solve for these variables. As long as you're only actually dealing with a single line, if that makes sense. So let's go ahead and do it. We're trying to figure out what line, what parabola, goes through these 3 points. Now, when I think about a point, what values, what variables do the numbers in the coordinate point represent? In a coordinate point, what does a coordinate point represent? X and Y. Beautiful. Yeah. X and Y. So what I'm going to do is I'm going to take each one of these individual points and create a line of equation, inputting the values for X and the values for Y, keeping A, B, and C as variables because those are the variables I'm trying to solve for. I'm not trying to solve for X and Y, I'm trying to solve for A, B, and C. So I have A times X squared, but first I'm going to input -1 as my X value, plus B times again X, so I'm going to input -1, plus C is equal to Y, which on this first point is 5. That's the first line of equation I'm going to create. The second line of equation that I'm going to create, technically it's the same equation, but now I'm going to be inputting the second point. I have A times this time 2 squared plus B times again 2 plus C is equal to my Y, which is -1 for this second point. Whoops. Then I'll repeat for the last point. And now that I have 3 lines of equations for 3 variables, I can use a matrix to solve for these variables. So I'm going to go ahead and create my matrix. Remember, a matrix, the first part of this matrix, is going to be the coefficients on the variables only. So even though that -1 squared is behind the A, it's still the coefficient for A. So -1 squared is 1. That's what I input first. Oh, maybe let's do the same colors. Let's be all fancy. Plus B times -1 means my coefficient is -1. Now, what is the coefficient on C? 1. Wonderful. Set equal to, again, that line isn't necessarily needed. It's just to help our mind focus, is the best way I can describe it, to 5. Then we have 4, 2, and 1 set equal to -1. We have 9, 3, 1 set equal to 13. So now all I have to do, get my, get my row reduced echelon form by going to second inverse math RREF, then alpha zoom 3×4 again, and input 1, 1, -1, 1, 5, 4, 2, 1, -1, 9, 3, 1, 13. And you get, when we row reduce this, 4, -6, -5. Remembering that the first entry is going to be our A, the second entry in that column is our B, and the third is our C. So I use those numbers to create the equation I was trying to find. A is 4, B is -6, and C is -5. And boom, I've created a quadratic. Isn't that so cool? I think it's so cool. So knowing this, you could have used matrices all those times in all those math classes where they were like, oh, here's 2 points, find the line. You could have used a matrix to find the line. Any questions on this one? Okay. So, and I asked the last class this too. Put a yes in the chat if you could do this on your own. Put a no if you'd like another example, because the second one, this next one, is the exact same thing. I'm just trying to gauge if I need to do it or not. So yes, if you could do it on your own. No, if you'd like to see another one. All right, beautiful. If this did trip you up, obviously I'm recording this right now. You can go back and watch it, okay? Also, I think Miss Sanders' class, has she posted videos for this? Day 2 notes? Okay, cool. Yeah, so you can go back and watch her video as well if you prefer her teaching style, or if I'm too like all over the place for you. All right, so there's one more type of problem they could ask you dealing with points. They could, instead of asking you to find a parabola, they could ask you to find a circle. Now, it works almost the same way. The only difference is, if I'm looking at this equation, the coefficients are not on my squared variables. They're just on my x, my y, and they are my constant. So what I'm going to do is I'm going to separate the variables I'm trying to solve for and the two terms that don't have variables I'm trying to solve for on them. Meaning, I'm going to take the x squared and the y squared and move them to the other side of the equal sign. Because remember, when I'm trying to do a matrix, I'm trying to get my coefficient matrix separate from everything else. So I'm going to separate these by moving x squared and y squared to the other side. And I'm going to actually put them on the right. It doesn't matter which side, but it'll make more sense in our head if I put it on the right. So I'm going to subtract them over. And it makes my life easier if I just group them together and think of them as a single term and subtract that single term. You could have subtracted them separately and put negative x squared, negative y squared, but in the end, it'll make my life easier if I just put a negative in front. So now, again, just like before, everything works the same. I have 3 points. I'm going to plug in the x values for the x's and the y values for the y's and create my 3 lines of equation. So first, I'm going to plug in 0, 0. So I have, let's see, I got to see my equation. I'm going to be zoomed out for a second. I'm sorry, but my memory's not very good. So I have d times 0 plus e times 0 plus f is equal to, now just because these are squared, it doesn't make anything any different. I'm still just plugging in the x and y values. So 0 squared is 0, y squared is 0, and there is no such thing as negative 0, so I just write 0. So now I repeat for my next point. Plug in 0 for x, and this time 5 for y. So I have 0 squared, which is 0, plus 5 squared, which is 25, but it's a negative 25. Then, again, I have 3 for x, 3 for y, and 3 squared is 9, 3 squared is 9, Add them together, it's 18, but it's a negative 18. So this is what I end up with. Oh, that was a messy. Okay. So then everything else works the exact same way. I'm now going to create my matrix. So I have 0, 0, 1 equal to 0. I have 0, 5, 1 equal to negative 25. And I have 3, 3, 1 equal to negative 18. And I put this all in my calculator. I get my rotor decessional form by hitting second inverse, going up to B, alpha zoom, 3 by 4, 0, 0, 1, 0, 0, 5, 1, negative 25, 3, 3, 1, negative 18. One, 0, 0, 0, 1, 0, 0, 0, 1. Ugh. It's okay, just deal with it, Miss Sunderland. Ugh. Oh, no, I can't do it. Okay. No. So, I'm now just going to take these and plug them into my original equation there, remembering that the first entry is D, then E, then F. So I have 0 is equal to x squared plus y squared minus 1x, which the 1 becomes invisible, so it's just minus x, plus, or sorry, no, it's negative 5y, and then there is no f, it's 0. And this is our equation. Now, unfortunately, Math Excel could ask you for the solution to this equation in standard form. This is in general form for a circle. How do we take this and convert it to standard form? Oh boy, you guys are usually much quicker than this. 7th period got it immediately. How do we convert this into standard form? Oh, 3 words. First one starts with a C. Third one starts with an S. Blank the blank. Ah, thank you. Not even someone from my class. I am so disappointed. You complete the square. You complete the square, guys. Okay, so would you like me to show you completing the square? Or can you complete the square on your own? Put a yes if you can do it on your own. Put a no if you would like me to show you completing this square. Okay, good. If I did just do it. Let me show you. I did just do it in 7th period, in case like you're too afraid to say no. This is the square completed. If you want to take a picture of that or whatever, it will be on my notes posted as well, okay? But yes, you are going to have to know how to complete the square sometimes on Math Excel. Unfortunately, they're picky. Sorry. All right. what time is it? 2:26, 3:40. Okay. So I think what I'm going to do, because we did do these in Algebra 2, and I was kind of planning on doing these word problems and stuff next class with my class. So I think I'm going to hold off on doing these till next class. And I think I'm going to go back and do the determinant with my class. Oh, I'm still in 7th grade. Go back and do the determinant with my class, and I'm going to say, Miss Sanders' class, you are free to go. I believe that I'll be seeing you again on Friday, by the way. So Miss Sanders' class is free to go. My class, we're going to finish up last class's notes. All right. Oh, and oh shoot, they all left before I said you could just watch her video to get the end of those. Oh well, it's okay. All right. So, remember last class, we found the determinant. Well, let's say this. We learned that if we know what the determinant is, we can know whether or not the matrix is going to have an inverse or not. If the determinant is equal to 0, it won't have an inverse. If the determinant is not equal to 0, then it will have an inverse. And remember, we found the determinant by taking the forward-facing diagonal, multiplying those terms together, and then subtracting the backwards-facing diagonal, multiplied together. That's how we found the determinant. To find the determinant on a larger matrix, it works the exact same way. It's just you are going to have multiple diagonals to work with, so it makes it a little harder. Now, all of this above is explaining another way to find the determinant. Have I ever seen this way before in my life? No. Every single professor I've ever had has done what I'm about to show you. And every other math teacher I ask says, oh yeah, in college we learned it this way, not this way. So neither one is harder. But I think because this is not the way that you'll see in college, I don't see a point in teaching it to you this way, if that makes sense. So I'm gonna do the diagonal way instead, because it's going to be what you see in college. All right, so remember, we added the forward-facing diagonal and subtracted the backwards-facing diagonal. So that's basically the bottom line of what we're going to do here. My forward-facing diagonals always start from the top left and go to the bottom right. So this is my first and dominant forward-facing diagonal. And because it's forward-facing, it's going to be a value I'm going to add to get to the determinant. Now, determinants, this is matrix B, are usually notated with absolute value symbols. I know we've used absolute value symbols like a million times for a million different things in math. Do I know why absolute value symbols are repeated so much when it's not always for absolute value? No, I think that they just kind of ran out of symbols maybe. But when you're dealing with matrices and you see absolute value symbols around a matrix, it means the determinant. Okay? So the determinant of B is equal to, now I'm going to take this forward-facing diagonal, and I'm going to multiply its values together. And it's going to be a value I add to get to the determinant. So 1 times -1 times 1. Then I find my next forward-facing diagonal. So I start on the very next number to the right on the top, and I go down to the right. Now notice, this is not a full diagonal. There are only 2 entries. Meaning what you're going to do is you're going to pretend like at the end of this matrix, it forces you to go back to the beginning of the matrix. So this diagonal goes from 2 to 3, and it actually continues to -1. And because this was forward facing, this is going to be a diagonal I add to my determinant. So I'm going to add 2 times 3 times -1. And then I find my third and final forward-facing diagonal. It's too blue. Now, I only have one number here. I need to continue back to the front like I did on the previous diagonal. So this diagonal includes -1, 2, and 0. And this was forward-facing, so I'm going to add it. -1, 2, 0. So now I've included all of the numbers, right? There isn't a number I didn't include in one of my multiplications, meaning I have now found all of the forward-facing diagonals. Now I need to find the backwards-facing diagonals, going from the bottom left to the top right. So let's do orange. The major backwards facing diagonal is this -1, -1, -1 diagonal. Because this is backwards facing, this will be subtracted. -1, -1, -1. I don't like this. Okay. -1, -1, -1. All right. So then we move to the right again on the bottom, because backwards facing starts on the bottom, or at least that's how I think about it. What have I not used? Red? Purple. So I start at 0, go up to 3, but that's only 2 entries. I need to find the third by going back to the front of the matrix and hitting up that 1. So now that diagonal has 3 entries. And because it was backwards facing, I need to subtract this. 0, 3, 1. And for my last, I start at 1, but that's only 1 entry. I need to cycle back to the front and hit up to 2. This was backwards facing, so I'm going to subtract it. -1, 2, 2. So now I'm just going to simplify all of this. 1 times -1 times 1 is actually a -1. Whoops, I want to do the same color. 2 times 3 times -1 is actually a -6. -1 times 2 times 0 is actually 0. Negative, -1, -1, -1 is actually a +1. Negative 0, 3, 1 is actually 0. And lastly, -1 times 2 times 2 is -4. So our determinant is a -10, meaning that yes, this matrix has an inverse. Now, if this was, oh, purple, Smith told me, yes, good. If this was just a normal problem, like if Math Excel had literally just asked it just like this, find the inverse of the matrix if possible, you could have just plugged this matrix into the calculator and hit -1. And if it gave you an answer, you would have said, yes, there's an inverse and this is what it is. The reason why I went over how to find this determinant of this big matrix is because Math Excel, one of the problems, gives you a matrix, sets it equal to its determinant, but does not include one of the entries inside of the matrix. It leaves a variable. So what you have to know is how to find the determinant so that you can then solve for that variable, which is nuts, right? But that's what Math Excel does. You would go about finding what you would do is you would, I shouldn't have erased that. You go about finding your determinant, leaving this x, simplifying, simplifying, simplifying. This is going to be a negative x, moving all of this to the other side and just solving for x, right? It's basically just a linear equation once you have set up the determinant. Do you know what I'm saying? Am I making sense? Am I being clear? Yeah? Okay. Sometimes I don't know. Oh, I'm not being clear. Oh, oh, like for, oh, yeah, no. We didn't actually find the inverse here, Isaac. Yeah. What we did here was we found the determinant. Because the determinant tells us whether or not there is an inverse, right? So I was just showing you how to find the determinant because on Math Excel there is a problem where it's set equal to a determinant and you have to solve for a variable. Okay? Oh my God. Oh my. Guess and check. Well, if it gets you through, I guess. All right. So there's one last problem I want to go over. It's actually really easy. I just have to mention it, okay? But right here, if we're trying to figure out if two variables are, I'm sorry, variables. If two matrices are inverses, remember, if they are inverses, what it means is B is equal to the inverse of A. And if they are actually inverses, it means that when I multiply matrix A times matrix B or multiply matrix B times matrix A, do you guys remember what I said it would equal last class? If they are inverses, multiplying inverse matrices will produce what? Uh, multiplying inverse matrices. So remember, like, well, it's kind of like this, right? These are inverses of each other. What will this produce? What does that produce? Huh? What does it produce? What is A divided by A? 1. Okay. What is the equivalent of 1 in matrix form? Oh, I don't want to just say it. Matrix, matrix. Guys, it's an identity matrix. An identity matrix. When you multiply two inverse matrices, it produces an identity matrix. Remember, an identity matrix has ones on the diagonals and zeros everywhere else. Right? It's the multiplicative identity for matrices. Anytime you multiply an identity matrix by a matrix, you get the same matrix. So when you multiply inverses, you produce an identity matrix. Right? This is what I sub 2 is equal to. So anyway, okay, what I'm getting at is to figure out if two matrices are inverses, all you have to do, multiply them in your calculator, and if it equals an identity matrix, you know that they're inverses. If it doesn't equal an identity matrix, oh my gosh, they're not inverses. But when we multiply matrix A by matrix B, it does produce an identity matrix, meaning, yes, I should say, A and B are inverses. Meaning, A is equal to the inverse of B. Whew. Are there any questions? Okay, I release you.